Okay. Thanks, to the organizers for this super nice workshop, and also for inviting me to give this talk. I must say that the talk is a bit of a challenge because there are many people in the audience who knows a lot about topological order or topological error correcting codes, and maybe there are others who never, ever in their lives heard about the toric code or things like that. So then I decided to introduce topological order in a kind of not very standard way for quantum information. And I will try to give more a flavor of the condensed matter kind of background of topological order. That, by the way, it was the origin of topological order. I mean, the very definition of topological order by when appeared in the understanding of condensed matter systems. Okay, so let me just, put the setup. We will be, considering regular lattices, let's say, for simplicity, the square lattice. And then in each kind of point of the lattice, we will have a particle, will be a spin S particle. And this essentially means that the local dimension of the Hilbert spaces in each of the sites is, 2S plus 1. Most of the cases, we can think of having, spin 1/2 particles, and this means that the local dimension is 2, so we have qubits, Okay, in nature, particles do not interact all with all, or at least is not the usual thing, because of course the interaction strength decay with distance, and usually decay very fast. So in most cases, one particle interacts only with those which are close by. And then, the interaction is nothing but, of course, a Hermitian matrix, that if, for instance, one particle interacts with another, there are 4 particles interacting, then R is equal to 4, and then the interaction is simply a Hermitian matrix of size d to the 4 times d to the 4. We will always assume also that the interactions are uniform, so that the kind of particles interact the same way with the close-by particles, no matter in which position they are in the lattice. And then if I consider one interaction H and I put it in the lattice position I, then I have HI, and the Hamiltonian is nothing but the sum of all these interactions. Okay? The Hamiltonian is just the energy observable, and it's the one that kind of governs the evolution of the system, as you probably know. No? Okay, there is one object important in this context, which is the ground state. The ground state is nothing but the normalized eigenvector of minimal eigenvalue of the Hamiltonian. And it's kind of the stable state, so the state that you get if you cool the system down to temperature equal to 0. Okay, even the aim of the talk is that even if the particles interact only with those which are close by, the entanglement in the ground state can have a very global nature. And this kind of global entanglement, which is called topological entanglement or topological order. And the talk is actually about this. How can it be that even if the particles only talk with those that are close by, if you cool the system, then what you get is an entanglement. It's pretty weird entanglement. It's a very, very global entanglement. And the nice thing is that this is not just a mathematical statement. That you have to cook up a super strange Hamiltonian in such a way that the ground state. No, there are very natural Hamiltonians in nature for which the ground state is topologically ordered. So these things, these topologically ordered systems are out there. Okay? And there are examples like the fractional quantum Hall effect states, high TC superconductors, some spin liquids, things like that. Okay? Good. Okay, so which is the aim of the talk? The aim of the talk is to, at least partially try to attack 3 questions. One is more historical, probably. So where does topological order come from? The second is a bit more mathematical, is how can one define it formally? So in the sense that one has really a definition of what topological order is. The third, of course, is then, now we know what topological order is, how can we construct examples of systems with topological order? And then, of course, open problems that you may be interested in thinking or knowing that are important, or some people working on them or whatever. Okay? Good. So before starting even to talk about topological order, it would be nice to talk about order. No? Because, what does order mean in this context? And then, so, the concept of order comes associated to the concept of phase. And what is a phase? Okay, so if you think of a phase of nature, then you think of ice, liquid, solid. You have water, and you increase the temperature, you decrease the temperature, and you know that there are different phases there. No? Okay, this is the picture. Now, how can we go a bit more in detail and understand which is the difference, for instance, between ice and liquid? Now, if we look at the particles in a liquid or in a gas phase, they move freely. They are completely disordered. But if we go to the ice, to the solid, they are arranged in a crystal, so in a lattice. And then just looking at this, one sees, or one immediately sees that these things are ordered. So there are some order here in the particles, where if you have all of them kind of moving around, there is no order there. So this is kind of the picture one has. So here the particles are ordered, and here they are disordered. How can one formalize the fact that in one case particles are ordered and the other they are disordered? And the nice thing is that one can do this based on symmetries. So you take water or gas, and then you take a piece of it and you move it. No matter in which direction, no matter how much, you find exactly the same thing. However, in the lattice, you can, to recover exactly the same structure, you can only move particles that, something which is proportional to the lattice distance, because otherwise you get something different. So in a sense, this system has less symmetry than this. In this, you can translate the system, arbitrary real distances, and here you have kind of this lattice distance. So you have less symmetry. And then essentially this is kind of the main thing, that you can understand that you are ordering more the particles if you are breaking some of the symmetries of the system. Yes?
But in the gas, it's kind of like a random assignment of locations, right? And then I would assume that there's no way how you can translate it so that you get the same again. So in what sense is it the same?
Because if you look at the system here and you look at the system here, you don't see the difference. You cannot see in which position you are by moving the...
Well, there might be some, I don't know, a random cluster here, and if I move...
No, but the gas particles are freely moving. There is no... So
I think this question makes sense, because so when you are saying that there is a translational symmetry for the crystal, right? So that assumes that the locations form like a group, and therefore you can talk about translational symmetry. But like in the gas, there is no topology, like there is no group a priori on the particles, so you cannot talk about like any symmetry of the ground state with respect to anything, because there was not that group start.
Statistical. Yeah, we're talking about statistical.
Yes.
It's not exactly right. You can't map exactly the molecules on the molecules, but statistics.
But then if I'm talking about the possible configurations in gas, so that I move and have another possible configuration, then this also holds for lattices, because a lattice that has the points here is as possible as a lattice that has the points slightly shifted. So
no, but the lattice positions are fixed.
Yeah, but then you could say the gas positions are also fixed.
No.
In a particular snapshot, they are fixed.
Never mind. I don't want to get stuck in this first slide because it has nothing to do with the rest of the talk. Okay. It's just. The way to understand which is order and which is disorder, and how one can motivate by the fact that there is some symmetry and some break symmetry. If you want, let's go to the quantum case, which is the next slide, and it's even more clear because, of course, this is. One cannot talk about ground state here because there is temperature. So ground state is something you need. These are kind of thermal states and things like that. So let's go to the quantum case if you want. And if you want to keep the discussion, let's keep the discussion here. Okay. So let's talk about the quantum case now. I'm only trying to get intuition of why some order is associated to some broken symmetry. I'm not trying to give now a theorem or anything like that. So let's now go to the quantum case. Quantum phases that occur at zero temperature. Okay. Now, of course, we cannot vary the temperature to change between the phases because we are at zero temperature. But we can vary the parameters in the Hamiltonian. And then by varying the parameters in the Hamiltonian, we can have a system which is ordered, like this one, in which, of course, it's clear that there is some order. The spins are all of them pointing in the same direction. We can have something different, which is a spin liquid. And a spin liquid is a state in which all symmetries are preserved. So it's a state in which the symmetry, you have translational invariance. Imagine that we are in both cases, we're in a lattice. So in this system, you can translate the system. Imagine that you are in a torus, so you can translate the system is invariant. You also have local rotation symmetry. So if you rotate all the spins with the same rotation, all of them, the system is also invariant. So it has all possible, you can also have if you rotate the system like that, it's also invariant. So you have all possible symmetries, again, in a lattice. And here it's clearly that you don't have all symmetries, because of course, if in this state you rotate all the spin at the same time, you get a different state. Okay? If you rotate all of them from up to down, you get something completely different. It's not clear at all from the beginning that this spin liquid system exists or not, but I mean, they exist, okay, at least in theory. But I mean, this is why they are called spin liquids, because they are the analog of the liquid in which you have kind of all symmetries. And this is, I mean, some kind of ferromagnetic state in this case, and you have some order here. So these are disorder system, these are order system. And again, the intuition is because, okay, you have some kind of, I mean, you see it and you see that the particles are ordered. And if you want to mathematically formalize it, the way to see it is that this local SU2 symmetry, so the fact that by rotating all spins in the same direction, this state is invariant, this state is no longer invariant under that. So there is a symmetry, which is this local SU2 symmetry, which is broken. So again, there is a connection between phase. This is one phase, this is a different phase, with concept of order. So this is order, this is disordered. And with a concept of a symmetry breaking. There is a symmetry here, which is broken here. And there is a third concept, which is how you detect that this symmetry is broken. And in this case, it's super easy. You just take the sigma C operator, okay, in one position, for instance, in this position, and you take the expectation value. In this case, this is 1, and in this case, this is 0. Okay? So there is a local operator, which even has a physical meaning, which is the magnetization per particle, that distinguishes both phases. In the disordered phase, because you have the symmetry, the observable is 0, and in the order phase, the observable is not 0. So, and this is called a local order parameter.
What's I?
I is simply one position, the one you prefer, because the system is traditional invariant, a single position. It's a sigma C in position I.
So when you say it's 0, you mean averaging over LIs? Or?
When this is 0, what I mean is if this is expectation value of this observable against this state. So.
But some of them are pointing up.
No, but this state, I mean, I cannot, of course, I cannot draw the system because I mean, it's just a pictorial thing of something that I cannot draw because it's a highly entangled state. I cannot draw a picture of it. Okay.
But that means that something that is like kind of like a cat state or something, where it's a superposition between all pointing up and all pointing down,
yes,
which sounds very ordered to me.
Yes.
But it would still have the expectation 0, right?
For this observable, yes.
Okay.
Yes, definitely. Yes. But it does not mean that. I mean, you can detect this phase, the fact that you have all up, all down, all down differently. But I mean. This state is very particular, the one of all up plus all down, because you have this plus and minus. But let's talk to this later if you want. But again, I'm trying just simply to construct some intuition of the concept of order and these things. It's not. I don't want to give a. Okay. So again, there is a local order parameter. So it's called order parameter because it's a parameter which detects the order, and it's called local because it's a local observable. End of the story. Okay. And then. This is the Landau approach to phases, is the following. So there can be different types of order, for instance, the ferromagnetic order, this one, antiferromagnetic order, in which the particles are aligned spin up, down, up, down, up, down, or other orders, like we will see others in the presentation. The nice thing is that they are characterized by a broken symmetry, and this broken symmetry is detected by some order parameter, which is local. And I mean, this approach to phases has been extremely successful in condensed matter, and essentially, I mean, up to the 80s, all phases, phase transitions, and whatever were able to be classified and studied with this approach. Okay? Yes?
So just make sure I'm understanding this correctly. Are you trying to say that if you want to distinguish between ordered and a disordered system, there always exists some local observable which will give that away, basically? It might not be Zi, but...
Yes. No, not always. I mean, not in the topologically ordered case. This is exactly what I'm going to talk about. Now, this is the topological order approach to phases. But now we will see that there are some phases, some states for which this does not work. Okay, this is kind of the. They are kind of like pseudo-topological, when is this all up plus or down, that have some of the feature of topological order, but they don't have others. We will see it if you want later when we talk about these things.
So you haven't actually defined what a phase is, right? You're giving us different ways of distinguishing.
Exactly, I didn't.
Because it's not defined.
No, it can be defined, but again, this definition, if you want a mathematical definition, is subtle. And if you want, I will give it at the end of the talk with a phase. It's essentially, okay. But so again, I mean, this is the way that condensed matter, I mean, usually think. I mean, they have examples. They give names to the examples, and they give similar names if the samples are similar, and then out of these, the mathematical physicists try to write definitions and then have to prove theorems and whatever. So I'm now in the condensed matter point of view of giving examples and giving names to examples, and with this we have an idea of why or how things are called, let's say. Okay?
And order is a property of the quantum state, or is it a property of the lowest energy space of the Hamiltonian?
Very good question. No, it's a very good question. In principle, in most of these, essentially in condensed matter, you always talk about Hamiltonians, and therefore it's a property of the ground space of the Hamiltonian, if you want. And this is exactly why this all up plus or down is not topological, because if you have a system with this ground state, you also have the ground state all up and the ground state all down, and they are topologically ordered. So it's kind of, for instance, you have an easy interaction or something like that. So this is clearly not topological, because in the ground space, you have product states. Even if you have a superposition which can have some features of being non-locally detectable, okay, like this. But anyhow, okay. So let's move to topological order. So in the 80s, there were two systems. One is the fractional quantum Hall effect, and the other is the high TC superconductor that kind of, in a sense, challenged this Landau view of understanding phases. We will concentrate on this high TC superconductors. We won't talk about high TC superconductivity at all, but we will talk about the resonating valence bond state, which was kind of one of the state that was postulated by Anderson to explain high TC superconductivity. And this is RBB, is resonating valence bond state. And then understanding this state is not easy, and there are many open questions even now. I will talk about some of them later. But there is even a simplification of this, which is called the quantum dimer model, that was kind of goes back to Roxanne and Kivelson, and I will talk about this quantum dimer model because it's one of the first places in which topological order appeared. So we have a square lattice, and then we have, whenever I draw something like this, a dimer like that, I'm thinking in a singlet. Okay, singlet is up down minus down up, or if you want 0 1 minus 1 0. Of course, in order to specify. I need to order, to have kind of directions in the edges in such a way that I specify the sign of that. But I will forget about this subtlety, so let's assume that there is a range order of the directions in the edges, and then therefore it's clear which is the first particle and which is the second particle in any of these singlets. And then I call configuration to a covering of the lattice. A covering means that I put these dimers in such a way that each vertex belongs to one and only one of them. Okay? There are different possible configurations. One is this one, for instance. Okay? One is this one. Okay, there are many others. The problem, one of the main problems to understand the kind of real resonating valence bond state that I will define in a while, is the fact that these configurations are not orthogonal between themselves. So then, what Roxanne and Kivelson said, okay, let's remove this problem, and we will, by definition, assume that these configurations are orthogonal. Okay. There is a second problem, and it's the fact that in your Hilbert space, there are, of course, states that are not configurations. And this is another problem, and they decided to also forget about this problem by restricting the Hilbert space to the space spanned by the configurations. And this is the quantum dimer model. The quantum dimer model is a model in which I have a Hilbert space, which is the orthogonal span of all possible configurations of the lattice. Okay? Yes?
So on configuration, you mean the tensor product of those?
Exactly, the tensor products of things like that. Exactly this. Exactly.
What do you call the orthogonal span of things that are not orthogonal?
No, because we made them orthogonal. We define a Hilbert space. Now we call this configuration an object. We forget for a while that these things are singlets, and we call them kind of red, dimers or red dimers or whatever. I forget where they come from. Even if I have in mind where they come from in order to give physical interpretation to the things I get later. But at least to understand, for the mathematics, I forget where they come from. Okay.
So we can think of them as particles that they are not.
Exactly, if you want, yes, but okay. And then I have a Hamiltonian, which is this quantum dimer Hamiltonian, which is this Hamiltonian there. It has two parameters. T is always positive, and it comes with a minus sign, and V can be both positive or negative. So let's see what this Hamiltonian does. So this, since it has a negative sign, I mean, this kind of put energy bonus if you resonate. Resonate means that if you have, I mean, two dimers like that, then you would also have them, you would like also to have them like that, okay? Because this gives you energy if you do this. I mean, not gives you, I mean, this removes energy if you do this. In this case, if V is positive, you penalize having two dimers in parallel, one close to the other, and if it's negative, you put a bonus on that. And this is the Hamiltonian, okay? So this is the resonating term, and this is the term that penalizes or not having dimers in parallel. Then we go to the limits. So let's take V over T goes to minus infinity. So this means that I'm taking V, since T is positive, I'm taking V negative and large, much larger than T in absolute value. And then, of course, if I have dimers in parallel, I mean, I have a huge energy bonus. So the system tends to put dimers in parallel. Therefore, in this limit, the ground state of the system is this column state. Okay, there are not just one, many columns. So the ground state is not unique, but one of them is this column state. Okay, so I have clearly an order system. It's a column order. Okay. If I go to the other limit, V over T goes to infinity, then V is now positive, and therefore I penalize a lot having dimers in parallel. So of course I have to avoid this, and I have this staggered order in which I do not have a single dimer in parallel to another. Okay? So there's a different type of order. It's clear that this is an order system, at least from the picture, but it's a different type of order. What happens in between? And this is the interesting case. So this is called the Ross-Archiverson point, and this is when V is equal to T. And in this case, the ground state of the system is the resonating valence bond state. The resonating valence bond state is the equal wave superposition of all possible configurations. And it's called resonating valence bond state because we make all dimers resonate in all possible ways. Okay, with this, and this is the point in which we have some topological order. So this is the thing we are interested in, and it's also the state that kind of was postulated by Anderson to explain high TC superconductivity. So the first thing is that this RBB, yes.
So on the left side, when you say row order, sorry, column order, row order is just as good, right?
Yes, of course.
But it's like the IC model. It sort of picks one of them.
Yeah, exactly. So the ground state is degenerate. You have this, you have also the translated data, you have the rotated. Yeah, of course. Yeah. I just picture one of them. Yes.
So it's known to be the ground state, or it's believed to be?
I mean, it's the usual thing. I mean, it seems it should be, no? Because this is infinite energy compared to this. So you can assume this is no longer there, and now you have only this term. It's clear this is the ground state.
But it's not like
it's only in the infinite limit. Yeah, if you want. Yeah, it's kind of There could be maybe perturbations around this. Yes.
If you have islands of vertical and horizontal, but large islands, that's also as great as energy.
Yes. No, this is I think rated.
You have that too.
Yeah, this is of course. Of course. I mean, I agree. I mean, if you go to the infinite limit in which you remove this, I mean, it's clear that this has the minimal possible energy. Of course, it's not the unique one, so there could be many others, like Ross, and there could be more complicated ones also. I'm not claiming they are not.
But I may ask at this RK point, when
What?
it's this, at this point,
Yes.
the RVB
Yes.
state
Huh?
is the ground state.
Yes. This is no.
This is not.
This is no. Yes.
Okay. I see.
This is not.
Well defined.
Sorry?
Yeah, sure.
This put a bonus. If you have something like that, then you should also have something like that, because this gives you an energy bonus if you do this. So we are concentrating in this point, and this is kind of in the original work of Ross and Gibson. They show that this is really the ground state at this point. Okay. So this state does not break any symmetry. Now we are back to the fact that in which we assume that these dimers are made out of singlets. Since they are singlets, they have SU2 invariance. So this we have for free. And this system does have also traditional invariance. Yes.
Sorry, so the RBB state is just
the equal wave superposition of all possible configurations.
so these are just tensor products of
Each one of these configurations is a tensor product of these things, and this is the equal ways superposition of 4 possible ways of putting the dimers in the lattice. Okay, it was postulated by Anderson to explain high superconductivity, and maybe I can even say a couple of words of why this has anything to do with superconductivity. And the nice thing is that it's a candidate for a new unobserved, up to now, but there are many candidates for that, phase in nature, which is a topological spin liquids. That this spin liquid is clear. The fact that it's topological is what I'm going to talk about now. Okay? So it has all the features of being a topological model. For that, indeed, one needs a frustrated lattice. So a square lattice is not good for that. So we need a triangular or a Kagome lattice. But this is not a problem because indeed there are real materials for which the natural lattice is a Kagome lattice. And this is an experimental paper, indeed, in which they show this. And the nice thing of the Kagome lattice is that it seems that the simplest interactions, the antiferromagnetic interaction, high symmetry interaction, gives the RBB as a ground state. So really, there are very natural interactions, the most natural one indeed, that gives this RBB, or seems to give this RBB as a ground state. And there is kind of a numerical paper of White and his group in Science showing this.
What's a frustrated lattice?
Good question. A frustrated lattice is, in most of these situations, our Hamiltonians have some antiferromagnetic interaction. Antiferromagnetic means that if one spin is up, the other should be down, the closest one. So you have in your lattice a triangle. This is impossible to satisfy at the same time in all bonds. You have a square. It's clear that I can put this up, down, down, up, and everyone is happy. But if I have a triangle, if I put here up and I put here down, I cannot make this node happy because if I put down, this is bad for that. If I put up, this is bad for that. So this is why if you have triangles, your lattice is called frustrated because you cannot simultaneously in these antiferromagnetic interactions make everyone happy.
So it's something like not too colorable.
Yes, exactly. If you want, yes.
Like not
Exactly this. Exactly. You want exactly this. Good. Okay. So then let's try to see, because I didn't define yet what topological order is, which are the special properties of this RBB that allow people to call it topologically ordered.
Sorry, but why do you need a frustrated lattice?
No, this will come. This will come later. I mean, I will try to give an idea of why. But okay, so okay, that's the direction. Okay, this. So which is the topological content of this quantum dimer model? So let's do a couple of very trivial things. So one is I'm going to draw 2 lines, one like that and one like that. And then I realize immediately that if I count the number of dimers that cut this line, in this case it's even, in both cases, 2, 2. If I take a different configuration, it's also even. And if I take any other configuration, it's also even. So this is always like that. Moreover, I can go from any configuration to any other configuration just by resonating moves. A resonating move is whenever I have 2 things in parallel, I put in parallel like that. Okay? So for instance, if I start in the column state, and I want to arrive to this one, then it's easy. First of all, I resonate these 2 to get these 2. I resonate these other 2 to get these other 2. And then I resonate with the middle one, no? To get this one, and I'm in this state. Okay? And I can do it to go from the column state to any other state. Okay? And the nice thing is that these 2 features can be changed, and they are changed if I change the topology, and this is why topological order, in which I put my system. So now I take a torus. A torus means that now, I'm also allowed to connect this particle with this particle. And then what I can do simply is, for instance, if I take these 2 dimers, I can move them up just one side, no? Like this. Okay. Now I have a dimer here, another dimer connecting the up with the down because I have a torus. I can do it, no problem. And then I see that, of course, now the number of cuts of this line is odd. It's no longer even. Okay. Moreover, this is also easy to see if you pay a bit. There is no way to go from this state to the previous blue one, so the one in which I didn't do this movement, by local resonating moves. No way. And then I get sectors which I call topological sectors, that are simply characterized by all states that are connected by locally resonating moves. So within each sector, I can connect any pair by locally resonating moves, and from one sector to another sector, I cannot connect by locally resonating moves.
So can you say again what's a local resonating?
It's simply, I have two things like that, I put them like that, and vice versa. That's it. Okay, and then one can see how these sectors are labeled, and here is where the frustrated lattice enter. If I have a square lattice, I have, many sectors, really. They are essentially, in an infinite lattice, there are infinite of them. Let's say there is no bound on that. If I have a triangular lattice, I have only 4 sectors. And this is the nice thing. So, and the sectors are labeled by exactly the parity of the number of dimers that intersect these reference lines. So this one and another one.
I don't understand whether you're talking about infinite or finite lattices, because everything that relates to parities doesn't make sense.
No. I'm talking about parity. What I talk about infinite is if I grow the lattice, what I mean is that the number of sectors grow with the system size.
Oh, okay.
And grow unboundedly with the system size. This is what I'm talking about, going to the infinite case, okay? But then what I do is I go to a frustrated lattice, so triangular or canopy, both are exactly the same in this case. And in this case, the number of sectors is 4. And they are simply labeled by the parity of the number of dimers that cut 2 reference lines. And they have the sector even, the sector even odd, the sector odd even, and the sector odd odd. And there are no more sectors. Okay?
So the parity is the same with however you put it.
Yes, it doesn't matter where do I put the line. Yes. And then the nice thing, because remember that I'm interested in the arcade point, so where I have the resonating balance bond state. If I have now this topology of a torus, then the ground states are, I have one ground state per sector. And the ground state is exactly the resonating balance bond state within the sector. Okay? So for instance, in the case of the triangular lattice, I have 4 sectors, so I have the degeneracy 4. Okay? And the nice thing is that, to know in which sector I am, I cannot detect it locally, because I have to count parity, and to count parity, I have to really go through a whole loop around the torus, and this is not a local thing. So I cannot detect in which sector I am by something local. I have to do some non-local counting to know which sector I am. Okay, and this essentially gives all the features of topological order. So let's see. Yes?
Can you explain one more time?
Yes.
What happened when you went to a torus that allowed you to shift?
Yeah, exactly. If I'm in a torus, I'm able to connect the upper particles with the down particles.
I see, and all the configurations have every node is connected to something, right?
Yes.
So, I see. So that's
right. Before I was not able to do this.
But you would be if you would have one more node on top and one more node on the bottom.
No, of course, the fact that it was even depends also on the size of the system, but it was simply that.
No, what I mean is you add just 2 vertices.
No, but of course then you have to fill the rest of the lattice also, of course.
So even in an infinite lattice, when you build your limits, you always consider square cuts of the lattice.
Yes. Again, this is just a motivation to understand the difference between putting a torus or not putting a torus. Of course, you can play with strange shapes and the properties will change. Okay. Yes?
So what sectors are just connected components in the configuration?
Exactly that.
Graph theoretically.
Exactly that.
And you might ask, well, not only like the connected components, but also if there is like a small cut that could be equally devastating or not devastating, whatever, as a complete cut, right? So with each sector could be like a bottleneck, which, you still can go through, but it would be very little. Right? So you are not concerned with this kind of thing, or?
So I think I didn't understand the question, sorry.
Well, so you consider the connected components of the configuration.
Yes.
And so each connected component is a sector. But now you might be concerned, like, how connected really is a connected component. So a connected component can have, well, it's either like an expander graph, or it can have a very small cut, which would be almost like
indeed.
falls apart.
Yes, indeed. In the square lattice, there are components in sectors with a single vector. For instance, these staggered faces they are the only, I mean, in the connected components, they are the only, it's just one point. So of course, the connected components in the square lattice can be very strange. There could be ones with many states and ways of moving, and there could be ones with a single state. So this is why the square lattice is not probably the right place to do this, and these frustrated lattices are much better, because in this frustrated lattice, I mean, things are much more robust, in the sense that there are many ways to go from one configuration to another. But of course, I'm not considering how fast can I mean, which is the number of moves I have. No, I mean, simply if you can or if you cannot.
You're not
Just,
considering the mixing problem.
yes, no, not at all.
What are the, so I understood the moves on the square lattice, but did you tell me, did you say what the moves were on the triangular lattice?
Yeah, sorry, yes, it's this, and this. And also in all the other directions. So this, you have more moves in the triangular lattice.
The two, sorry, it's hard for me to see the red thing. Two parallel lines?
There's these two parallel, and these two parallel.
So if two parallels are filled in next to each other, you can flip?
Exactly, yes. So you go from these two to these two, from these two to these two, you have more freedom. So then, let's try to distill from here what we could define as topological order. Okay. Here. So first of all, the degeneracy of the Hamiltonian, which is constant means that it does not depend on the system size. In this case, it's 4. Depends on the topology. If I put it on a torus, or if I put it on a plane, or whatever. Second, all ground states are indistinguishably locally. So you cannot tell in which ground space, in which ground state you are by any local observable. You have to really go through a non-trivial loop on the torus to count the parity. To map between the different ground states, you need a non-local operator, as we did in this case. To go from this sector, the even here, to the odd sector, we need a non-local move, which is this whole column. We move one up. Okay, in this case, of course, it's not very long because it's just 2, but it could be very long, and then it has to be something very long. Okay, so you have to change. I mean, there is no way. So the only way to go from one sector to a different sector is to do some operation on a non-trivial loop on the torus. In this case, it was kind of going up just every dimer from the beginning to the end. Okay. Okay, and these are the kind of the 3 things that appear there. There are another 2 properties that one kind of would like to have in a topological order model. One is another energy gap in the Hamiltonian. So this means that I have my ground state, and then there is, I mean, the next eigenstate of the Hamiltonian has energy, I mean, which is above the ground space, but this energy does not close. I mean, this gap in energy does not close with the size of the system. And why is this important? Okay, this simply, I mean, it's not really crucial, but the thing is that this enforces that your topological phase is robust, in a sense. Of course, if you take your system super big, and then very close to your topological states, you have a product state, because it has also almost minimal energy. I mean, how can you say that your system is topological if it's something that is almost the ground state, which is a product? No?
Yeah. So yes. Maybe this is related to Mario's question. So, if these configurations are perfectly, they're very well, if they're not very well connected, if there's a bottleneck in this chain you could get by doing these swaps, you can imagine there would be a very nearby state that's not quite ground, but it just involves flipping in the other side of the bottleneck, and then you would not have much of an energy gap.
It could be, yes. Indeed, you have it. Yeah, you can even make it kind of.
I know this naturally happens in translation invariant systems, but
I mean, this is a good question. It won't happen in all these quantum dimer models are known to be gapped, at least for the Kagome lattice. So this won't happen. I don't know if the lattice is not regular, or I mean, probably many weird things can happen. But at least in this regular lattice, in the Kagome lattice, which is the one which is best understood, and it's known to be a gap in this quantum dimer model. So, and indeed, it's exactly the toric code state. So there's a mapping to the toric code. So it's really the same that happened in the toric code happened in this quantum dimer model.
But what happens when you assume something that they're orthogonal even...
Good point. Yes. Let me... Okay. Okay.
I'm willing to delay.
No, I mean... I mean, if you mind to delete to the very last slide, because I will talk about this in the last slide. It's okay if you want me to say something now. I mean, okay. So
Sorry, can I stop you one more time? Gap. So there are various. So I'm trying to understand the scale of a gap. So what are we talking about in terms of violations of any one of these?
I mean, in principle, the gap is the gap. I mean, you have your Hilbert space, and then among this Hilbert space, you would like to see.
I think what he means is that in terms of V and T.
Yes.
So
No, but V, we are in the
minimal gap in terms of V.
No, V and T is they both.
V and T or just V plus T or something.
No, V and T are equal, both of them, because we're in the arcade point, and you can assume them to be equal to 1, because of course this changes the energy scale. So the important thing, you fix T and V, the important thing is that the gap does not close when the system size grows.
So it's constant.
There's a lower bound. It can oscillate, but there's always a lower bound, which is uniform in the size of the system. This gap can depend on V and T, but it's not a problem, as long as it does not depend on the size of the system.
And why is it constant? Why do you want it to be just constant?
The degeneracy, no, it's not clear. This is why I put brackets. This is what happens here, and this is what happens in most of the topological models in 2 dimensions. But as we know, in 3 dimensions, with this cubic code, this is no longer there. So no, this is why I put it in brackets. But yes. Sorry?
Are all of these conditions independent? Like, is 4...
This is a extremely good question. It's not clear at all.
Actually, related question, what's actually the difference between 2 and 3? What's the
Good. So let's take this all up plus all down, and the all up minus all down. If you take the reducibility matrix of both, it's the same. So they are locally indistinguishable. But you can map from one to the other just with a single sigma c in a side. Okay? Questions? Yes?
I just wanted to ask you, does it make sense to have a ground space that has both topologically ordered and not topologically ordered states?
This you want to avoid, because essentially you would like to, this you would like to avoid. Of course, you could have it, there's no problem with that. And this is what happens in the square lattice, and this is exactly what you want to avoid. In the square lattice, you have RBBs, which are very topological in the ground space, but you also have these staggered states, which are product states. And you would like to have only topological states if you want in the ground
So
space.
may I ask why you want to avoid it? I mean, what's the goal? Is it for application?
Maybe it always after this, I don't know. You could call, the thing is that what you call topological order, the Hamiltonian or the state. And this is also not clear, because there are features that are of the state, there are features of the Hamiltonian, there are features which are, first if you talk about excitations, you need a Hamiltonian for that. But to talk about these things, you only need kind of to have 2 orthogonal states which are locally equal. So, depends very much on this. Yes?
I guess the possible answer is that you're trying to construct such Hamiltonians in order to understand possible such topological orders, and it would just be simpler if you just have one type.
Yeah. In this case, you have a Hamiltonian for which all ground states are topologically ordered, and you engineer this Hamiltonian and you cool it down. What you get has topological order. If you have some product states, you can do all these things to get the 0 state in the end. Okay.
So if I understand right, the motivation is that that physicists are thinking of making some magic material, which, when put in the fridge, will exhibit certain topological properties, and therefore we need that there's only a topological ground state, because otherwise in the fridge it might do something else.
Yes.
Is that right?
This could be one thing, but it's not. Yeah. Of course, this topological thing depends on your perspective. If you have, in condensed matter, you have a concrete Hamiltonian, antiferromagnetic Heisenberg in the Kagome, you would like to understand the ground state. This is the usual thing, no? You can have a more quantum info perspective. You want to construct real states to do something with them, like error correcting force or topological quantum computation. Depending on your aim, of course, even which is the best definition change. So I give one in which I put most of the features that people call topological, let's say. But this is even the definition is something that you can discuss. Okay, so I won't talk about these excitations because otherwise I won't talk about anything else. But this is kind of why if you want, someone is interested, I can tell you later. But this is why there is some superconducting thing going on the RBB. Okay, why it's related to superconductivity, but I won't talk about this because otherwise. So what I would like to do in the next minutes is, to first of all talk a bit. Okay, we have all these properties. that we kind of distill out of a single example. And we like to see which properties do arise from there in the sense of pattern. If you have all of these or some of these, what else do you get for free? And then, is there a systematic way to construct systems with these properties? We have this argument, but can we construct systems with this type of properties, and how? And how weird can we make them? No? So, related to the first question, so which are the implications of topological order? So, first of all, it's kind of both are kind of the head and tail of the same coin. So, topological order systems are robust. Okay, this has been proven by Bradley, Hastings, and Michalakis. And the idea is, though of course this idea is really, I mean, a bit misleading, but is that, okay, if I have a topological system and I encode my information in the sector in which I am, if I want to switch sectors, I have to do something non-local around a loop of the torus, and this seems to be kind of unlikely that something like that happen. Of course, this is completely misleading, it's indeed false, but this is kind of one idea you can have in mind of why these topological states are robust. But of course, if it's difficult to go from one sector to another, I mean, there is of course something related that then these systems are difficult to create. Because of course you have to kind of encode something which is pretty global in the system. And then there is a nice result by Bradley, Hastings, and Verstraete that show that to create topological order with a time-dependent geometrical local Hamiltonian, one needs a time of the order of the size of the system. Okay? And the proof goes via Lieb-Robinson bounds, but I will try to give a flavor of the proof. I mean, just changing this time-dependent geometrical local Hamiltonian by quantum circuits that are geometrically kind of restricted, so that one qubit can only interact in the circuit with those which are close by. Okay?
So is it necessary that topological order is robust? You mean that if you add a small perturbation?
Of course, yeah, there are two types of robustness. One is the one they prove, that is if you have your Hamiltonian and you put a perturbation in any one of the elements of the Hamiltonian, then essentially, I mean, your system is kind of well connected to the original system. So the gap is preserved. This is what they proved. And there is the robustness related to thermal noise. And of course, we know that many of the systems, like Tori code, is not robust against thermal noise. So of course, there are two different types of robustness. But so yeah, this is kind of.
What's the second type?
Okay, if you put thermal noise. So if you have your, I mean, you are never at zero temperature. So if you increase the temperature, then excitations start to appear in the system with some probability. And since for most of these models, or at least in the 2D models, to move an excitation costs no energy at all, the moment you have one, you can move it around the torus, and you are out of the game. And you get excitations no matter how small you take the temperature, as long as it's not equal to 0. And in all these 2D systems, essentially, for any temperature still bigger than 0, you essentially lose the topology, more or less. More or less. At least, okay. Some of the features of the topology, at least. Okay.
So the difference is that one is local perturbation, the other is not.
Exactly. No, okay, no, yeah. You can see it like that if you want, yes. Okay. So let's try to prove this. It's pretty simple, the proof. So imagine I have my spins arranged in a lattice, 2D lattice, but for simplicity, let's take a line. The proof doesn't change at all. It's simply that it's easy to paint like that. Okay, and then I start with a non-topological state, and I want to create a topological state. Okay, then since psi1 is topological, there exists an orthogonal state psi2 to it, for which for all local observables they give exactly the same expectation values, because they are locally indistinguishable. Now what I do is I start up there with psi2, and I reverse the circuit, U daga, okay, or star, and I get another state which I call psi 0 tilde. Of course, psi 0 tilde is orthogonal to psi 0 because it's acting with the same unitary in two orthogonal states. Of course, unitarity doesn't change orthogonality. And now we will see in the next slide that indeed now psi 0 and psi tilde has exactly the same expectation values for all local observables. And therefore, since there exists another orthogonal state with the same expectation value for all local observables, this means that psi 0 was already topological in the first place. So, did you follow the argument or no?
That's under some assumption on you.
No. Okay, we'll see exactly. Assumption. Exactly, we will see that as long as u, so the depth of the circuit is smaller than the system size, this will be true. Okay.
But you say that within for a certain depth u, you cannot get from a topological to a non-topological. Is that what you were saying?
Or vice versa. Yes.
But for big depth u, you can.
Yes, for big depth, yeah. As long as the depth is the order of the size of the system, you can.
But then I could do it again and again and again, and I mean, getting from here to here consists of doing small steps, and at some point it has to flip from topological to not topological.
Of course. I mean, yes, yeah, I completely agree. So the thing is, yes, I completely agree. I mean, so the only thing is that, of course, what I'm saying is that if so the only thing that this proves is exactly what it proves. Okay, so that if there is another orthogonal state to this, that such that this both are exactly equal for all observables, local observables, and this depth is geometrically local, and the size of the depth is less than the size of the system, then the same happens for psi 0 and psi 0 tilde. I must say that the fact that there is an orthogonal state that has the same local observables, in principle does not imply that the system is topological, because the same happens for these all up versus all down things. I mean, you have all up plus or down. I mean, this GSC type state. This also takes time to create. I mean, geometrically local. So I mean, it's true that this does not give really the topologically order, but this gives exactly what it gives, nothing more. Yes.
So in this slide you have changed gears, and I am not sure.
Yes.
I won't understand.
Yes.
After you answer, but let me ask anyway. So the lines mean just the interactions in your grid, and so that these are those fixed interactions that you talked in the previous.
No. This is time. This is time. So these are my qubits. This is time, and these are unitary gates. It's a circuit. This is a circuit.
How does it relate to your what you have said previously, like those local interactions?
No, it has nothing to do with. Indeed, what I'm trying to show here is the fact that these topological states now sum anything with these properties. Doesn't have to do with the resonating valence bond or anything. I mean, any state which has these properties will be difficult to create. In the following sense.
If you just assume a two-dimensional thing, so the picture should have been three-dimensional.
Every layer is two-dimensional.
Yes.
That's what I was thinking. Every layer is two-dimensional.
Yes, this exactly. So this should be a 2D lattice, and this should be interactions on the 2D lattice. But for simplicity, I'm drawing a line.
So my other question is that you don't insist on the exact same interactions that we saw in the previous picture, or the.
No, this can be any.
Gates could be any gates.
This can be any gates. Yes, any gates. As long as they are unitary. Yes.
Simply with any gates, you cannot duplicate the ground state of the system of the previous slide. Is this
with a constant depth? Yes.
What circuit you build, but it must be local, but you cannot create the ground state of the system we saw in the previous
Exactly.
slide.
As long as this is not small. Let's say yes.
Are you trying to prove that the depth is equal to the number of qubits?
So?
What are you you're trying to prove the depth?
Yeah, exactly. I'm trying to prove that this depth should be the order of the number of qubits if I start with a product state, for instance.
And are you assuming that the gates can only interact with?
Yeah, geometrically local. Yes, I'm assuming geometrically local. Yes.
And in the case of a 2D lattice, do you still get linear, or do you get square root?
No, I get linear in the. So if I have L times L, I get L. So. Okay, so the proof is super simple. So what I'm going to show. So I I want to show that A psi 0 is equal to A psi 0 tilde psi 0 tilde, and then I know that psi 0 is U daga psi 1, and that psi 0 tilde is U daga psi 2, and then I want to see that this is equal to this. And then the only thing I need to show is that U daga is still a local observable. Because I know that psi 1 and psi 2 gives exactly the same expectation value for any local observable.
Can you define what a local observable
is? Anything, any observable that acts in a contractible region. If I have a torus, I have a region which is contractible. Any observable which is supported in a contractible region. This is local. That's the only thing. Okay? So it does not wrap around the torus. That's the definition. And then it's pretty easy because what I do is I draw U daga A U. So this is U daga. This is A, which is local, and this is U. Okay? And then since one is the daga of the other, things start to cancel. So this cancel with this cancel with this cancel with this, and then I don't have any of these three, and then this cancel with this cancel with this, and so on and so forth, and I get exactly this. Okay? I have a kind of a light cone, and then of course, now this is a local operator because it only acts in these lines. No? The rest is the identity. So, I mean, of course, to go from here to the end of the system, since this is a light cone, I need that this depth is proportional to the size of the system. And that's it, essentially, okay? I use it pretty easy. Good. Again, I mean, this is only sort of topological order because there are some states, like these GSC type states, like the all up plus or down, which have kind of the same feature if you want to start in a product state, let's say. So, okay. So now, I won't be able to talk about this. Okay, so I would like to say just 3 words about how to construct topologically ordered systems. And for that, probably the best way, all known examples fit into this language of PEPS. And then, okay, just one slide is about, I mean, PEPS is something to understand it, I mean, to really understand how it works, you need some kind of notation which is graphical. And it's this box leg notation for tensors. So, I mean, I have a box with one leg, then it's a tensor with one index, which is a vector. Okay? You have a box with 2 legs, it's a tensor with 2 indices, which is a matrix. Then, joining legs is tensor contraction. So, for instance, if I have 2 vectors, and I join the legs, this is just the scalar product, because I identify the indices and I sum over them. Then I have 2 matrices, and I join these legs, then I identify the column index of A with the row index of B, and I sum, and this is matrix multiplication. And then if I, for instance, sandwich a matrix between 2 tensors, then I get this sandwich, no? This expectation value of A against B and W. No? Now, if instead of 2 legs I have 3 legs, I can understand this as a sequence in I, in this leg, of matrices in the other 2 legs. And then if I draw something like that, then what I do is I fix the value of these indices. Then what I have is matrix multiplication and then a trace, because I'm identifying the row and the column index I'm summing over. So this picture up there is nothing but the sum of the trace of AI1, AI2, AN of the canonical basis vector A1, A. And this is called a matrix product state.
A matrix what?
Matrix product state, because it's a state which says that the coefficient is made out of product of matrices.
Product?
Product state. Okay. The same can be done in 2 dimensions. Forget about this now. So in 2 dimensions, now we have a tensor with 5 legs. So up, down, left, right, and I have another leg which is coming out of the blackboard. And then, if I contract through a 2D lattice, I get a state, and this state is called a PEPS. And then, the way to understand topology in this PEPS is the fact that you have a gauge symmetry. So the fact that this tensor, there is, for instance, a finite group, let's say G equal to C2, so that the tensor is invariant under acting with, for instance, C, 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 C. So only this property gives rise, essentially, to all the topological features of the PEPS. Only this property. And okay, to see it, I would need another talk, so I was very, very optimistic in preparing this one. So, but this is kind of what one can show. And one of the crucial steps is that one can make these loops, these small loops, grow. For instance, if I take two tensors and I apply this equality, I get C, 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 and another here, and the middle one cancels. So I get a loop which is bigger than the previous one. And I can make this bigger and bigger to show that any contractible loop vanishes. Non-contractible loops don't vanish, even if they can be arbitrarily deformed, and these non-contractible loops are associated to the different ground states in the Hamiltonian, which are locally equal. Okay. And okay, excitations are open strings, and one can understand many of the things, but okay, like the new statistics and things like that, so if you're interested, I can explain to you later. So let me just go back to the questions, or at the end of the question simply, and then, one can create more and more weird models, just changing the fact that you have these kind of local tensors by something which looks more global, but they still have the property.
Sorry, what is the restriction on what is the restriction of the symmetry? That G should satisfy what symmetry?
No, that you have some representation of the group that is invariant under the tensor. If you apply here some UG, UG dagger, UG, the tensor is invariant under that. This is a crucial thing. But now you can go beyond the group scenario and ask for more general kind of mathematical structures which behave similarly. That you have some kind of global symmetry, which is not group-like, but it still has the property that if you have one like that and one like that, it kind of glue and you get some bigger loop. Because this is a crucial property to get a topology, this gluing and getting bigger loops. And there are, for instance, in Hopf algebras, you get something like that when you have kind of twisted groups with elements of the third cohomology group. There are many weird mathematical objects in which you get this type of gluing things. And it gives, of course, more and more weird topological models.
But what is the condition on the groups that gives you topological order?
All finite groups give you topological order.
Except for identity?
Oh, no, any non-trivial group, of course. The trivial group doesn't, but any non-trivial group gives you topological order. Any finite one, okay? And then, of course, the question is if one can classify all possibilities. So is there a way to classify all possible symmetries that has this kind of glue and grow property of loops? I mean, is the only possibility to get topological order in PEPS this thing, or is there a different mechanism? And most important, is there a PEPS in any topological phase in such a way that if one understands what happens in PEPS, one understands what happens in all topological models, and finally what happens in the 3D case. So this is kind of all this kind of program of trying to classify topological phases, and I think PEPS is one of the probably the most, the best approach nowadays, because essentially it englobes all known topological models. But of course there could be ways, I mean, things out. Okay, there are more open problems related to the resonating Madison state, which are related to the fact that in the real case you don't have orthogonality of the symmetries. And there are many problems arising from there. And the first problem is that in principle there is no Hamiltonian even you can write up having the resonating Madison state as ground state. Okay, but this is again for questions offline because I'm out of time. So thank you very much.
Go ahead. So you say the RVB is a wave function looking for Hamiltonian. You said that it was the ground state of
No, but this is the real RVB now. I mean, the other one was the simplification of assuming everything is orthogonal. I am assume that I'm in the, and this is the real one. I have a really spin, have particles everywhere, and I take the resonating valence bond as the real equal superposition of singlets, now real singlets everywhere.
Okay.
Is there a Hamiltonian for which this is the unique ground state up to the fourth, the fourth degeneracy coming for topology? Okay. We showed indeed in 2012 that there is one, but and it was this was improved by Zhou and others in this year. But these Hamiltonians act on a whole star. Of course, they act on 12 sides, which is pretty big. So it could be that even the antiferromagnetic Heisenberg has the RVB as ground state or something close to RVB. Mm-hmm. So the thing is, if one could give better Hamiltonians, and even for those we don't know if they are gapped or not.
Okay.
So.
Can you also use quantum groups for this symmetries?
Of course. This is exactly what I wrote here. It's exactly this is the Haar integral. This is the commultiplication of a finite dimensional quantum group. This is antipodes, and these are representation.
Okay, so you need it all.
Yes.
Okay.
Yes. So this is exactly this. Yes.
And for Lie groups, it might not lead to.
It's not clear how to make it with continuous groups. For finite group is clear. If the group is continuous, it's not clear at all how you do this.
And you have examples where it doesn't lead to, or it might.
I mean, the construction doesn't work.
Doesn't work. Okay.
Yes. But apart from that, yeah.
So am I right to understand that basically the groups are fundamental groups of the space, and what you call topological order are you're counting the homotopy classes of your space? Because the moves, there are homotopic moves where you can find all the homotopic equivalent spaces when you start from somewhere. When you say they can't move between places, that's because you have a basically equivalent class of all the holes in the space. I don't know if this is like formally known or.
Formally known, not. There are connections with homology, but no, it's not clear to me now that there is.
Because you said with the toric code is Z2.
Yes.
Because that's just like the fundamental group, but you take the formal product, it's not a free group Z2, but if you take the formal product, it is something that looks like this for the torus.
I don't know. I mean,
so the groups here are acting on the spin space, and actually even not quite that, but not on the spatial structure anymore. So there's, there's the local
represent the spatial structure with your spin things.
No. So the local particle has some internal Hilbert space which is totally disconnected from the geometry. So those are two totally separate things. And this is the group he's talking about is more acting on the local particle rather than the spin.
So you have highly non-trivial things even in the plane. I don't know if this you can have all this non-abelian braiding in the plane. I mean, you don't need a torus for that. So,
they're not totally different things, but like one is simpler than the other. Because, I mean, certainly the homology group is relevant to the bigger question, but there is more into that than just the homology group itself.
Yes, it's clear, of course, that the number of, for instance, the number of holes is related to the degeneracy of the Hamiltonian, and you count kind of at least in the abelian case, you count exactly by the number of holes, let's say. In the non-abelian case, there are more things related to the structure of the group itself, and not just of the topology that count. So there is some relation, but I don't know if there is. I mean, how neat this is known.
Okay, if that's all the questions for now, let's thank David again.